Okay, this next example, we introduce one-dimensional kinematics. So we oftentimes will use kinematics to think of projectiles, of things moving. These are the very standard equations that you would see in a freshman physics class. We have, or even a high school physics class, we have our position function. So here, S naught would be our initial position. V naught would be our initial velocity, and this g right here, it says it down here, g is the acceleration due to gravity. So this would either be, depending what units you're using, metric we're probably more familiar with here. This would be 9.8 meters per second squared, and if we're using feet and seconds, this would be 32 feet per second. So depending on what problem we do, like in a moment when we get to example 4 here, we have feet as our units in place. So make sure that, and at your final answer, if you do replace in g for one of these two values, just make sure you pick the appropriate unit. So for example 4, we'd want to make sure we pick 32 feet per second squared, not the metric 9.8 meters per second squared. Okay, and then we have a velocity equation, which is your initial velocity minus your gt. So this is assuming that we have some sort of projectile that is moving up and down vertically. Okay. Now it is true that we could, imagine like firing a cannon or something, or shooting a bullet in the air or an arrow, and this thing will actually travel in, 2 dimensions. It's going to move upward vertically, and it's also going to move in that direction that we shot it. But in Calc 1 here, we're only going to be talking about things falling up or down. And it's true that something could be thrown, but we are only going to be worrying about its vertical motion, not its horizontal motion. Okay. So example 4, a stone is thrown vertically upwards. Let's go ahead and add something in here. This should have been in here. Let's add the language from the ground. Okay. Because if I don't add this, then you would probably wonder what the initial position is. So let's just assume it's from the ground with a velocity of 80 feet per second. And then we want to know what is the maximum height reached by the ball. Okay, and then we also want to know what is the velocity of the stone when it is 96 feet above the ground on its way up, and what about when it's 96 feet above the ground but on its way down. Okay, so let's go ahead and fill in some blanks here. We know that our initial position is the ground, so we're going to just say 0 feet for that. Our initial velocity was given to us, and that's 80 feet per second, so we can go ahead and use that. And then I won't write down what g is because it's right here, and we'll only really use that at the very end of the problem. We're not going to use that right now. Okay, so let's go ahead and work on this first problem, and that is, what is the maximum height reached by the ball? So I'll just call this part A, and I'll just say max height. So an important thing that is obvious when we actually say it out loud, but it is going to be the key to figuring this out, is when you throw something up in the air, eventually it will stop, right? It will stop, and then later it will fall back down, which is obvious, but there's an important thing that happens right here. When something is traveling upward, the velocity is positive. When something is traveling downward, the velocity is negative. So when something is at its maximum height, that means it's no longer increasing its height, but it hasn't yet begun to decrease its height. It's in that sweet spot. Well, this is another application of the intermediate value theorem. If we know the velocity is positive at one point in time, and then at a later point in time it's negative, since velocity changes continuously, it can't just go from a negative number to a positive number. It first must pass through 0. So we know the maximum height happens when the velocity is 0. So that's always going to be your ticket to figuring out what the maximum height is, or when the maximum height occurs. So let's go ahead and fill in our equations here. I guess we can do this right underneath here. So let's go ahead and just say that S of t so far is 80t minus a half gt squared, and V of t is 80 minus gt. You are more than welcome to plug in 32 right now. I'm in the habit of not plugging in until the very end. It honestly doesn't matter a ton. It really doesn't matter. So, yeah. Some problems, it's definitely easier to not plug in numbers until the end. All right. So that's what we know. So then for this part A here, the maximum height, well, we know that we're going to go ahead and look for when the velocity is 0. So if we go ahead and do that, we can go ahead and take the velocity, v, and set it equal to 0. So we have 0 equals 80 minus gt. We can solve for t to get 80 over g. That is the that is the time that the maximum height is achieved. So this is the time in seconds at which the maximum height occurs after being thrown. Okay, so this is, you want to keep in mind, this is not actually the maximum height. This is, we needed this to figure out the time. Now that we know when the maximum height is achieved, we can go ahead and plug in our time into this equation. So one thing we can think about here is that these two equations, they tell us different information. This one tells us heights, this one tells us speeds, velocities. Both of these equations speak the same language, though. They are written in terms of time, t. So if we get information about position, we can't necessarily directly import it into the velocity equation. We first have to somehow take this information we know about position and translate it to a time. And then we can take that time and plug it into this equation, and then we can sort of get velocity information out of it. We just did that exact same process, but here we started with information about the maximum height. We knew that the maximum height happens when the velocity is 0. So using that information, we can go ahead and get a t value out. So this is the t, the time that corresponds with the maximum height. So then we can take this and plug it into the position equation to finally get our answer for this. So we can then go ahead and just do S of 80 over g. And then we do that, we'll have, let's see here, 80 times 80 is 6,400 over g minus 1/2 g, and then we have t squared, so we have another 6,400 over, what do we have here? G squared. Well, we got a little simplification here to make. One of these g's will cancel with this one, so we'll just get a single g in the bottom, and then we have something take away half of that same something, so this should simplify into just half of 6,400 over g. 6,400 over g, so half that would be 3,200 over g, and that would be feet. But then here, if we actually plug in g is 32, then we do end up getting 100 feet as the maximum height. Okay. The next part here is we're asked what the velocity of the stone is when it is 96 feet above the ground on its way up. So we are given information about position. So we're going to go ahead and look at our position function, S of t, and we are going to go ahead and set that equal to 96. And if we set that equal to 96, we'll have 80t minus a half gt squared. And since we're going to have to solve for t, I'm going to go ahead and plug in that 32 right now for g to get minus 16t squared. So if we divide everything by 16, we should get, if we divide everything by 16, we should get 6 equals 5t minus t squared. And if we just rearrange this, we can go ahead and make this say t squared minus 5t plus 6. And then we can factor this in order to solve, and we get t minus 3 and t minus 2. So we have t equals 2 and t equals 3 for our two t values. So apparently at these two times, the ball is 96 feet above the ground. So just using some physical intuition, this would be 96 feet on the way up, and t equals 3 would correspond to 96 feet on the way down. So we can go ahead and just figure out what the velocity is. V of 2, if you plug it in, you end up getting 16 feet per second. And this makes sense because it's positive, so it's definitely going up. And V of 3, we end up getting negative 16 feet per second. So this is, I'll just say, upward. It's on the way up. And this is our downward velocity on the way down.